In the last lecture, I had briefly outlined the meaning of what is a belief network or a Bayesian network. So, in this lecture, we will look into the Bayesian network in details, and also try to understand that why do we require such networks and what are the things that we can infer with it. So, when we talk about reasoning under uncertainty, then what we have is we have a set of events, and some events can be causally related to other events with certain probability, because there might be certain other factors which we do not know of. There can be certain other factors which we know of, but we do not know the exact degree of influence that it has. So, all these unknowns or partially known factors can be modeled in the form of probability, and we can reason under uncertainty once we have some idea about those probabilities. So, we can effectively what we are interested in knowing about is the joint probability distribution. In other words, that suppose I have events x1, x2 and x3, then I am interested in knowing the probabilities of different combinations of this x1, x2 and x3 in practice, right. And we are also interested in finding out the probability of one or more of these variables, given that the other variables are true or false. So, for example, we might be interested in knowing in our alarm, burglar's alarm example, that what is the probability that John calls when there has been an earthquake, right. So, there, given that the earthquake variable is true, we are interested in determining the value of probability of John calls, right. So, effectively we should understand that what we have is a set of variables, let us say x1, x2, x3, and we are interested in the joint probability distribution. So, we are interested in things like p x1, x2, x3, right. Now, this distribution actually encompasses the probabilities of setting these different random variables to zeros and ones. So, for example, this distribution will be able to give us the probability that x1 equal to 0, x2 equal to 1, x3 equal to 0, right. It will also be able to give us the probability of x1 equal to 1, x2 equal to 0 and so on, right. It is also going to be able to give us the probability of x1 and x2, and what is this? This is the probability of x1, x2, x3 plus probability of x1, x2, x3 bar, right. And from the same distribution we should also be able to find out what is the probability of x1 given x2 and x3, right. Okay. So, we know mechanisms of the elementary probability to compute each of these, provided we are given the distribution of x1, x2 and x3. Now, is it clear how we can deduce each of these? Right. Now, Bayes network is a succinct way of representing this distribution. So, let us see what is the succinct way, how can we reduce the size of this representation. Now, if we did not know about any of these relationship between these x1, x2, x3, suppose they were all we do not know about their intercausal relationships, and we store this probability distribution explicitly, then what is the size of the distribution table for a set of variables x1 through xn? It is going to be 2 to the power of n, right. Why? the size of this is going to be 2 to the power of n, because that for each, see these x1 through xn can take the values of true or false, these are propositional variables, right. So, we can have a true or false set to each of them. So, the number of entries in the distribution table is going to be 2 to the power of n. So, this is a n dimensional table, right, and we will have 2 to the power of n entries in it, right. Now, storing that kind of a information is quite difficult. So, people try to see whether if we know about the intercausal relationships or we are able to deduce the intercausal relationships, then can we get a more succinct representation, right. And to do that, let us first look at the way in which we can rewrite this joint probability distribution. So, what we have is probability of x1, x2 through xn. We can write this as probability of x1, right, given x2 through xn times probability of x2 xn, right. And then we can again rewrite this, we can unfold this term also in a similar way. So, if we do that, then what we are going to have is probability of x1 given times probability of x2 given, this is x3 to xn, and so on until we have probability of xn minus 1 given xn times probability of xn, right. Now, there are several ways in these individual terms can be simplified. For example, if we have a case where we have some p of xi given xi minus 1 through xn, xi plus 1 through xn, and if it turns out that xi is independent of all these variables. So, this is going to reduce to simply p of xi, provided that xi is independent of all these, right. Also, it could be the case that one of these, one or more of these variables subsume the others, because let us understand in what ways can they subsume. So, we will introduce a terminology called conditional independence. So, we will have this kind of scenario when it is totally independent, but we will also look at a scenario where it is conditional independent. Now, for example, if you recall that we had that burglar's alarm example, we had alarm here in the network, and then we had two causes for the alarm, possible causes. One is an actual burglary, and the other is earthquake. And the effect of the alarm is again can be two. One is John calls and the other was that Mary calls. Right. Now, let us look at the probability of John calls given alarm and burglary. Right. Now, see, my claim is that I can rewrite this as probability of John calls given only alarm, and my claim is that if you know that the alarm has gone off, then it does not really matter whether the burglary has taken place or not, because the John calls is affected only by the fact whether the alarm has gone off or not, right. So, for John all it matters is whether the alarm has gone off or not, right. So, if you are given that the alarm has gone off, then the probability of John's calling is not dependent on whether the burglary has actually taken place or not, right. So, therefore, this is a scenario of conditional independence. It is this alarm that actually subsumes this burglary, and so you do not require this burglary anymore in the conditional probability, right. So, it is this fact that we know that John calls when he hears the alarm. It is this fact which has prompted us to say that okay, if alarm is known, then John calls is independent of burglary, right. Now, these are the kinds of things that we attempt to discover from the domain and use them to reduce the size of the conditional of the joint probability distribution, and the net result of that is what we have in Bayes networks, right. We try to order the variables in such a way that we can make maximum use of these conditional independence, so that in each of the tables that we store in the besides the entries of the Bayes network is less, right. Now, let us do one thing. We will we will return to this example and see what happens if we use a proper ordering and what happens if you use a improper ordering. Okay. So, let us recap. The example was that we have a burglar alarm at home, right, which responds to burglary or earthquakes. There are two neighbors who on hearing the alarm calls the police. John always calls when he hears the alarm, but sometimes confuses the telephone ringing and then also calls, and Mary does not always call even when the alarm goes off, because Mary is fond of loud music, right. Now, this was the belief network example that we were looking at. So, in this case the ordering of the variables is John calls, Mary calls, alarm, burglary, earthquake, right, or Mary calls, John calls, alarm, burglary, earthquake, right. This is the ordering in which we are considering the joint probability distribution, right. So, effectively what we are doing is we are starting with probability of John calls, Mary calls, alarm, burglary, earthquake, and then rewriting this as probability of John calls given Mary calls, alarm, burglary, earthquake. Now, if you are given alarm, then all these others are irrelevant, because John calls will depend only on the alarm, right. If the alarm was not given, if we do not have this variable here, if it is unknown, then this may not be independent. Then the fact that Mary has called is increased evidence that the alarm had went off, suppose alarm was not here, suppose we had only John calls given Mary calls burglary and earthquake, then the fact that Mary had called is increased evidence that the alarm had gone off, right. So, then John calls and Mary calls are not independent, but given alarm they are independent. Are you getting my point? Right. And then we have probability of Mary calls alarm, right. So, this the first term will reduce to probability of John calls given alarm only, right. Now, let us look at what we can do with the second one. The second one will be Mary calls given alarm, burglary and earthquake. So, again if the alarm has gone off, if we know about the truth of the alarm variable, then burglary and earthquake do not matter in terms of Mary's calling, right. I mean not in this case, of course it could have been the case that when Mary also detects the earthquake and hears the alarm, then she might infer that it is a false alarm which has gone off, but we are not talking about that, right. So, in this case again this alarm renders Mary calls to be conditionally independent of these two. So, again we will have okay, and we had another term out there which was and that term can now be expanded right, and therefore, what is going to happen to this alarm given burglary and earthquake. Now, here none of them can subsume the other, even if we know that there is no burglary, the alarm can go off because of the earthquake and vice versa. So, this does not reduce any further, right. So, we will again expand up this to probability of B given E and probability of E. Now, this term we know that the probability of burglary has got nothing to do with whether there has been an earthquake or not. I mean it is true that burglars will not be willing to do a burglary when there is an earthquake going on, but well for the example that we are having here, we will consider this to be independent. So, this is going to reduce further to probability of burglary, right. So, the total thing that we have, let us see, will be probability of John calls given alarm, probability of Mary calls given alarm, then probability of alarm given BE, and then these two. Now, this is exactly the Bayes network that we have. So, we have the parent of John calls is the alarm, parent of Mary calls is the alarm, parent of alarm is burglary and earthquake, and burglary and earthquake are the top level events which are not causally dependent on anything else, right. Now, let us see what happens if we try some other ordering. Suppose we look at the other ordering where we have the ordering that we are going to look at is earthquake, followed by burglary, then alarm, so this is exactly the opposite of what we took last time, followed by merry calls. Right. So, let us start constructing the belief network with this in mind. So, we will have earthquake here. And we will be looking at probability of earthquake given burglary, alarm, John calls, merry calls, right. So, now let us see, does earthquake depend on burglary? Can we make it independent of burglary? We are trying to find out the probability, we are trying to reason about the probability of earthquake given burglary, alarm, John calls and merry calls. Yes, isn't it? So, therefore, this is not going to be independent. So, we are going to have will alarm affect earthquake? Yes, right, because whether the alarm has gone off or not is increased evidence. If the alarm has gone off, then it is increased evidence, however minor, of the earthquake having taken place, right. Then let us look at burglary. Okay. Now, given alarm, I think the earthquake will be independent of John calls and merry calls, right. So, then let us look at burglary given alarm, John calls and merry calls, right. The probability of burglary, for the same reason, it will depend on alarm, right, but given alarm it is not going to depend on John calls and merry calls, right. Then let us look at alarm given John calls and merry calls. Right. Now, we are going, this is going to depend on this definitely, this is going to depend on this definitely, right. But what about probability of John calls given merry calls? It depends, right. So, this is going to be the belief network. Now, this is not much different in size as compared to the original belief network, right, but it requires us to produce probability values which are very confusing. For example, we have to produce the probability value of earthquake given burglary. So, how are we going to produce that kind of probability, right. So, if we construct it in an incorrect way, then problem number 1 that comes up is that you are required to specify the conditional probability of some very confusing combination of events, which is very difficult in practice. There is another problem. So, let us look at a slightly different ordering, where we have alarm burglary okay. Now, let us start with this one. So, we will have first of all alarm, it will depend on burglary of course. Are you, is it clear to you why the alarm becomes conditionally dependent on burglary? Right. Then we have earthquake, John calls and Mary calls. Now, let us look at the different kinds of things that we will have. Okay. When we look at alarm, given burglary, earthquake, Mary calls, John calls, right, this is going to have, is going to be dependent on all of these. None is going to subsume the other, right. We will have earthquake to burglary, and then we will have the ones that we had previously, namely these three. We will also have from Mary calls to burglary and Mary calls to earthquake and John calls to burglary and John calls to earthquake, right. So, this is going to be the Bayes network for this ordering. Now, see, the problem here is that if you look at the conditional probability table here, because I have 4 parents, so I will have to store 2 to the power of 4 entries here, right. This fellow will have 3 parents, so 2 to the power of 3 entries here. So, these conditional probability tables are going to be quite large, because you will have many parents of the same node, right. So, if you use an improper ordering, this is another side effect that takes place, but it is not, we can always say that this particular one and this one and the one that we started off with, they are all valid Bayes networks, in the sense that we are able to recover, if you are able to produce the probability tables for these, the conditional probability tables for each of these, then we can recover the joint probability distribution from all of them, right. We can recover the joint probability distribution from all of them. So, all of them are valid representations of the joint probability distribution, but in this case we were having to produce conditional probability values which are not natural and which are difficult to obtain experimentally, and in this case the size of the representation is quite large as compared to the one that we had started off with, right. So, from here let us now, from what we have seen so far, let us quickly see the way in which we can construct a Bayes network. So, the way in which we have talked about right now. So, we first choose the set of relevant variables that describe the domain, then choose an ordering for the variables, which is, as we now know, is a very important step. While there are variables left, pick a variable x and add a node for it. The way in which we did was, we started from x1 and then picked up x2, then picked up x3 and so on. Set the parents of x to some minimal set of existing nodes such that the conditional independence property is satisfied. Define the conditional probability table for x, right. So, this is the way in which we can construct a Bayes network. Okay. As we have seen that conditional independence relations play a very important role in the Bayes network structure. So, we will now formally make some definitions about conditional independence, which will be very useful when we start querying the Bayes network. The first step is to construct the Bayes network. Then what? Why do we construct the Bayes network? We construct the Bayes network because if we have any queries related to the joint probability distribution, which includes queries like, okay, if I have a cavity and if there is a past history of extraction, then what is the probability that I will have to go for extraction again, right. So these are the kinds of diagnostic inferences whose probabilities we want to evaluate, right, and that is what we are trying to do using the joint probability distribution. So far we have only studied how to construct the Bayes network. Next we are moving into how to use the Bayes network to infer about other combinations of events. Okay. If every undirected path from a node in X to a node in Y, X and Y are sets of nodes, right, in the Bayes network, is d-separated by a given set of evidence nodes E. Evidence nodes are the nodes whose variable values are given, like when we say that probability of John calls given alarm. So, alarm then becomes an evidence node, because we are given that alarm has gone off, or probability that Mary calls given not alarm, then also alarm is an evidence node, right. So, if we have a set of nodes X and a set of node Y, and every undirected path from X to Y is d-separated, we are going to define what we mean by d-separated, by a given set of evidence nodes E, then X and Y are conditionally independent given E. Okay. Now, the definition of d-separation is like this: a set of nodes E d-separates two sets of nodes X and Y if every undirected path from a node in X to a node in Y is blocked given E. Okay. Now we have to define what is blocked, right. A path is blocked given a set of nodes E if there is a node Z on the path for which one of the three conditions holds. Z is in E and Z has one arrow on the path leading in and one arrow out, right. Okay. We are going to come back to this, right. I will first give some examples, then it will be easier to understand this. Okay. Just keep this in mind, that a path is blocked given a set of nodes E if there is a node Z on the path for which one of the three conditions holds. That is, that the node Z is in E and Z has one arrow on the path leading in and one arrow out, right. So, it is like this, that we have in the path a node Z and one arrow is leading into Z and one is leading out of Z, right. Then this path is blocked by Z, okay. Or Z is in E and Z has both path arrows leading out. So, it could be that, see, in a Bayes network you can have paths like this also. This is also a path. Say if we take this path, right. Now, in this path, this Mary calls is one which is d-separating or blocking this path, because it is in the evidence set E and I have two edges coming out of the node Z. So, this is one scenario. The other scenario is that the path has Z like this and the path is like this. So, the path is okay. It is not necessarily a directed path. Then neither Z nor any descendant of Z is in E and both path arrows lead into Z. So, we have Z and both path arrows are leading into Z and neither Z or any of its descendants are in E. So, the path is like this, but this is not in E and neither of its successors are in E, right. Now, these are the cases where Z blocks the path, and we say that if Z blocks the path, then the set of nodes E deseparates two sets of nodes x and y if every undirected path from a node x to a node in y is blocked given E. Let us take an example. We have the following scenario. We have a car radio, we have the car battery, we have the ignition, we have the petrol gauge, and we have the event whether the car starts or not. So, for example, if the car does not start, then it could be that either the petrol it is out of petrol, or it could be that the ignition is not working properly, or it could be that the battery is down, right. But if the battery is down, then the radio will not work either, right. So, if the radio is working, then it is evidence, increased evidence that the battery is fine, right. So, this is the set of events that we have and the base network structure is given here. Now, whether there is petrol and whether the radio plays are independent given evidence about whether the ignition takes place. Suppose we are given that the ignition takes place, right. Then whether there is petrol and whether the radio plays will become independent. Now, is it clear why? Is it? So, formally the node ignition, which is part of the evidence, will deseparate the radio and the petrol. So, the path from radio to petrol is deseparated by ignition, right. So, this is which of these cases? Out of these cases it is this one, right, because the node Z is in E and this is the node ignition, we have one arrow coming into it, one arrow going out of it. But is it intuitively understood that why radio and petrol are independent once we know whether ignition has taken place or not? See, because if ignition has taken place, given that ignition has taken place or not taken place, right, then the probability whether it starts or not is not going to depend anymore on the battery. If you know whether the battery is good or not does not matter anymore, because we are given whether the ignition has taken place or not, right. So, the probability of starts becomes independent of battery. Similarly, the probability of whether there is petrol or not becomes independent of battery and of radio. Petrol and radio are independent if it is known whether the battery works. Again for the same reason, right. If you are given whether the battery works or not, then petrol and radio will be independent, right. Petrol and radio are independent given no evidence at all. Yes.
Shouldn't radio dependent on ignition?
No, radio is directly from the battery. It doesn't go through the ignition. You can run the radio even when your car is not, you have not turned on the ignition.
But doesn't ignition show that the battery is working?
Yes, but if you know about the battery status, then radio and ignition become independent. So the dependence is through the battery, and that is how we have depicted it here. In the slide, if you look in the slides please. If you look at the slide, then we have slides, yes, that the dependence between radio and ignition is through the battery, right. Now, if you do not know about the status of the battery, then obviously radio and ignition are dependent. But if you know about the battery status, then they are independent. Then the radio has got nothing to do with the ignition, right. But petrol and radio are independent given no evidence at all, right. If you do not know of any evidence, then they are independent. Why? Because starts is going to deseparate them. So you do not know, if you do not have any evidence about whether the car starts or not, then you cannot, there is no dependence between petrol and radio, right. However, if you are given evidence about the car starting, then petrol and radio are not independent. Why? Because if the car starts, right, then the radio not running will have less probability, right. And also why are petrol and radio going to be dependent once we know whether the car starts?
Car starts with petrol. The probability of having petrol is less than.
If the car does not start but the radio is on, then that is increased evidence that we are out of petrol, right. If the car starts, if the car does not start but the radio is working fine, then that is increased evidence that we are out of petrol. So petrol and radio are not independent anymore, right. So now we have seen the example of all three of these deseparating scenarios, right. Okay. So please recap this thing at home and try to think of some events where you have these kinds of separations, right. When we do the tutorial, we will do one example on Bayes network. Okay, let us see what we have next. If the car does not start, then the radio playing is increased evidence that we are out of. This is what I just now said. Okay. Now we are interested in doing different kinds of inferences using belief networks, right. I am just introducing them today and we will pick them up from here in the next lecture. So one is diagnostic inferences, where we try to find out, go from effects to causes, right. Like for example, given John calls, we can infer that probability of burglary given John calls is 0.016, right. So this is from effects to causes. We can also have causal inferences which are from causes to effects, like probability of John calls given burglary or probability of Mary calls given burglary. See, for example, when we are talking about medical diagnostics, right, then a diagnostic inference will be that if you are given evidence about the causes, then what is the probability that this is going to be the effect, right. And when you are talking about causal inferences, then given the symptoms, what is the probability that this is the disease, right. Okay, then intercausal inferences between causes of a common effect. So given alarm, what is the probability of burglary given alarm is 0.376. If we add evidence that earthquake is true, then probability of burglary given alarm and earthquake goes down to 0.003. Why is that so? Because earthquake itself is a very rare event, right, and the probability that you are having a burglary at the same time as the earthquake takes place is even less probable, right. So, this is the between causes of a common effect, if you want to reason about. Then mixed inferences, like setting the effect John calls to true and the cause earthquake to false, gives probability of alarm given John calls and not earthquake is this, right. So, in terms of Bayes networks, these are, how are these dependent? Okay. In the first one, in diagnostic inferences, we are inferencing the probability of a parent given the child. The second one is inferencing the probability of the child given the parent. In the third one, in intercausal, we are examining the probability of a parent given a child and a sibling, right. And in mixed inferences, we are examining the probability of an event given its parent and its child, right. So, these are the four main kinds of inferences that we will talk about, and we will examine some algorithms such that given a Bayes network, how do we determine these probability values. Okay. So, with that we come to the end of this lecture.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape, and IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. with the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theatres, and from the quiet fibre-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed